This is Module 2, Video 1. In this video, we're going to define the adjacency matrix for a network. We're going to define the degree matrix for a network. We're going to discuss the handshaking lemma. And we're going to define the incidence matrix for a network. The adjacency matrix for a network is a square matrix, meaning the number of rows is equal to the number of columns. In the adjacency matrix, each row represents one of the nodes. Each column represents one of the nodes. So, for example, in this case, we have 8 rows and 8 columns. Let's look at the first row. There is a 1 in position, the first row, the second column. That's because node 1 is adjacent to node 2. Node 1 is not adjacent to any other node, so the remaining entries are all 0. For our second example, let's look at node 2, just to clarify. Node 2 is adjacent to nodes 1 and 3. So if we look at row 2 that corresponds to node 2, there is a 1 in columns 1 and 3, and zeros elsewhere. The same will hold for each column. Now recall that we're using the notation K sub u to represent the degree of node u. So if we look at each row or each column, the sum of the row should be the degree of that node, because the number of ones would indicate the number of neighbors. So for example, if we look at node 4, and we look at row 4, we see that there are exactly 3 ones in row 4 and exactly 3 ones in column 4. And the ones are located in positions 3, 5, and 7. And those are the 3 neighbors of node 4. Our next matrix is the degree matrix. Unlike the adjacency matrix, which is a relationship between 2 distinct nodes, the degree is a measure of a single node. Therefore, the degree measures are the measures down the diagonal, and we have zeros elsewhere. So again, if we look at row 4 or column 4, we have a 3, because node 4 is degree 3. It is the only node of degree 3, and that's the only 3 on the diagonal. Now you might think, well, why have a matrix for that information where you've got zeros everywhere except for the diagonal? But we will see that we use this matrix in various matrix equations to obtain other numerical values for the network. Now the incidence matrix. The incidence matrix is different from the adjacency matrix and the degree matrix in the following way. The adjacency matrix and the degree matrix were both square matrices. But the incidence matrix is not a square matrix. It is an n by m, where the number of rows is the number of nodes, and the number of columns is the number of links. So unless you have the same number of links as you have nodes, it's not going to be a square matrix. So let's use this graph to illustrate the incidence matrix. Since the nodes are numbered, it's easy to see that we have 6. So we should have 6 rows. Now how many links, how many edges, that will tell us how many columns. This is a good place to introduce the handshaking lemma because we want to count the number of edges. So the handshaking lemma is written below, and on the left we see it's the sum, 1 through n, of k sub I. Recall again that k sub I is the degree of node I. So on the left, what we have is just the sum of the degrees. Now, if we consider, say, link H. Link H connects node 2 and node 5. In the sum of the degrees, we will be counting link H when we add the sum into the sum, the degree of node 2, and we'll count H a second time when we add into the sum the degree of node 5. So link H will get counted into the sum exactly 2 times when we add in the degree of node 2 and when we add in the degree of node 5. And this is true of every edge or every link. It gets counted exactly twice. So by the time that we've counted or added all of the degrees, we'll come up with a sum that should be twice the number of edges. So if we add the degrees in this particular graph, we have 4 plus 4 plus 4 plus 4 plus 4. 5 4s are 20. And then the last node has degree 2, so we have 22. That tells us that the number of edges should be 11. And so our incidence matrix is going to be a 6 by 11. So let's begin constructing our incidence matrix. We have 6 rows and 11 columns. Now if we look in the first column, that represents edge or link A, which is incident to nodes 3 and 6. So in rows 3 and 6, we'll place a 1, and we'll have zeros elsewhere. To fill in column B, how many 1s will we have? Exactly 2. Each column will have exactly 2 1s because each edge is determined by exactly 2 vertices. So if we look at link B, it's incident to nodes 1 and 3. So we'll have a 1 in row 1 and a 1 in row 3. And zeros elsewhere. So I think you can easily continue this and place 2 1s in each column in the appropriate place. Now what about each row? What is the sum of each row? Well, each row would indicate what that vertex or node is incident to, so the sum ought to be the degrees. So if you look at row 6, you get a sum of 2, and that is the degree of node 6. So again, we often, when using a computer to work with a network, we can provide the network or import the network into our software by a matrix. And then the matrix is used to determine all the other properties of the network. So we now know the following definitions. We know the adjacency matrix for a network, the degree matrix for a network. We've discussed the handshaking lemma. It says the sum of all of the degrees in the network should be twice the number of edges. And the incidence matrix for a network.